Greetings to all and welcome to this lecture. Today we are going to start two-terminal MOS structure. Here we will discuss about the flat band voltage. In this lecture we will see what is contact potential, meaning when two different metals are in contact, then there will be a potential developed between it in no bias condition. We will also see what will happen if multiple metals or materials will come in series. Then we will start our basic case or fundamental block of MOSFET, which is a layered structure called a MOS capacitor, meaning you have a metal here, an oxide layer here and a semiconductor. This layered structure is called a MOS capacitor, metal oxide and semiconductor capacitor. Considering what is the gate voltage applied to it and what is the condition for flat band, we will see in this coming lecture. These are the learning outcomes of the lecture, which will help you to understand the contact potential and how the contact potential is helpful to analyze the MOS capacitor. So, the materials are defined by different properties. In general, if two different materials have been taken, then the electron energy will be different, and hence when you make a contact of these two materials, there will be a charge transfer. Even if you will not apply a bias, then the electron will transfer from either to M1 to M2 or M2 to M1. Thus, there will be a potential exist between that which actually restricts its flow and causes an equilibrium. To characterize a material property, there is a work function which tells us how easily an electron can leave its host material. In general, we will measure the work function from a Fermi level reference. So, this is a Fermi level for a metal, or you can consider it as a material, and this is a reference level. Reference level is the energy level correspond to the electron which just leave its parent atom or host atom or host material or a parent material, right. In general, we represent it as by 0 electron volts. This value is called a work function. So, work function is defined as the minimum possible energy which is required for the electron to leave its host material. If the work function will be higher, it means what? It is tightly bound, the electron is tightly bound with that particular material, and hence you need to apply more energy. If it is low work function, means the electron is loosely connected with its parent atom, and hence you require a less energy. Generally, this work function is represented in terms of volts, but as we know that the potential energy and the potential of electron can be represented in opposite way because of minus q direction or minus q charge, right, because of negative charge. So, this work function can be represented as q times of phi m1 or m2. In this case, let us consider my work function of m1 is lesser than work function of m2, which is shown here, because with respect to reference energy ER, this height is smaller compared to this height. Once you join this material m1 and m2, what will happen? The electron will go from m1 to m2, and this flow will continue until there will be a potential exist between m1 and m2 such that this flow gets stopped, and hence equilibrium should established, right. So, we will find that the potential of m2 will be lesser than potential of m1. It means it is like the electron was coming from m1 to m2, this become more negative, and hence this potential will repel the electron to go back to the metal m1, and hence equilibrium established. This potential developed between m1 and m2 is called a contact potential. In general, this contact potential can be given as the difference between the work function of the metals. Here phi m2 represent the work function of metal m2 or material m2, and here the work function of material m1. Why I am saying material, not metal? Because it is not necessary that m1 and m2 can only be metal, it can be semiconductor, and we will see this case. Before that, you have seen here that m1 and m2 joint here, there is a contact here, but this reference is air. So, is it necessary that always this reference will be air? No, we can use any reference material to measure the contact potential, but we will see whether we can measure the contact potential by a voltmeter or not, that we will see. So, if you connect this reference material with M1, there will be a contact potential between this reference material and M1. Similarly, there will be a contact potential between this reference material and M2. If you write a KVL around the loop, ultimately what will happen? Phi of Wm1 plus phi of M1 M2 plus phi of Wm3. If following this definition, which says that the contact potential is nothing but the difference of work functions. So, phi M1 minus phi of W plus phi of M2 minus phi of M1 plus phi of this is M2. So, phi of M2 minus phi of W. If you see around the loop, the total potential is 0, right. Now, as I said, that is it necessary that M1 or M2 will be metal only? It can be semiconductor. So, what if it is a semiconductor? Then we need to know what is the work function and how do we calculate the work function. As we following the definition of work function, the work function is defined as the minimum energy to remove the electron from its host material. So, which level I should choose to measure the height or the minimum energy with reference to energy. So, in general, in semiconductor we choose the Fermi level as a reference with which we say that this is the work function. So, for a work function of a semiconductor, it can be defined as the energy difference between the Fermi level and the reference level. Now, why Fermi level? Because the Fermi level is a chemical potential level which shows that the probability of occupancy of electron is 50%. Second, the Fermi level is most relevant for the energy transfer because the high energetic electrons are possibly occupy this Fermi level under equilibrium. So, we need to get this height. To get this height, it means the difference between Fermi level to reference level, we can just bifurcate in few parts. One height is what is the difference between reference level and conduction band. This can be represented as chi, where chi is known as electron affinity. Electron affinities can be defined as how easily the semiconductor accepts the electrons, right. This is a known value for silicon, it is nothing but 4.05 electron volts. Again, if you are representing in energy, you should multiply with electron to make it electron volt. If you are representing in volts, you can just simply write 4.05 volts, right. This is the y axis is energy. The another bifurcation to calculate this complete height between ER and EF is this much. This we know, it is half of EC minus EV, which is nothing but half of band gap EG by 2, and this height is additional height we need to add to actually calculate the total work function of a semiconductor. So, a work function of a semiconductor for a p type material is can be given as chi plus Eg by 2 plus phi f. It means this phi f is nothing but difference between EI minus EF, right. So, this difference is called phi f, which is nothing but Fermi potential. Fermi potential. From our base and understanding on the band diagram, we can simply relate this difference between EI minus EF with respect to doping of that p type material. So, the doping of or p type material doping or the whole concentration can be written as Ni exponential of EI minus EF divided by kT, where this can be written as EI minus EF is equals to log of P naught by Ni. This is P naught. P naught stands for whole concentration under equilibrium into kT. If I want to represent in terms of voltage, I need to divide by Q. This quantity kT by Q is thermal voltage, which we are going to represent by phi t. So ultimately this Ei minus Ef can be written as Kt by Q log of P naught by Ni, where P naught is nothing but acceptor concentration. So this is doping dependent parameter phi f, right. For a p-type semiconductor, until and unless stated otherwise, we will consider this Fermi potential as positive for p-type material. Now what will happen in n-type material? In n-type material, the Fermi level is close to the conduction band, correct. It means if we want to measure this work function, it means the difference between the ER and the Fermi level, it can be written as chi plus Eg by 2 minus of phi f, because the Fermi level goes above the intrinsic level, or this is the work function of a semiconductor which is n-type. Now what will happen if it is degenerate semiconductor? In a degenerate semiconductor, for example, it is P plus. If it is P plus, we know that the Fermi level is aligned to valence band. So here closely Fermi level will come, and hence you need to take a height or total values of the difference between reference level and the Fermi level. So ultimately the work function of a p-type semiconductor under degenerate condition is can be given by chi, because you know ER minus EC is what? Chi plus Eg or Eg by Q. If it is an n-type degenerate semiconductor, you have a reference level. So this is a reference level, this is conduction level, conduction band edge, right, and the Fermi level is nothing but aligned with the conduction band edge, and this is EV. So this distance, this minimum distance is your electron affinity, and hence the work function of n-type semiconductor which is in degenerate means heavily doping, you will get the work function as chi, right. We will use this work function to calculate different parameters like what is flat band voltage and all. Now the next question is, what will happen if different materials will be in series? It means I am connecting different materials in series and I want to calculate what is the effective voltage between this terminal K and L. So if there are different materials in series, there will be a contact potential between these contacts. So here the contact potential is nothing but what? Phi M2 M1. Here the contact potential is what? Phi M3 M2, and so on. Here the contact potential is what? Phi Mn Mn minus 1. And I am interested in what is this psi KL. Psi is the potential between K and L. If I am going to write a equation, potential balance equation along the loop, then we will get psi KL is equals to phi M1 M2 plus phi M2 M3 and so on, phi Mn minus 1 into Mn. Using the basic formula of contact potential, which is nothing but the difference between two work functions, this is can be written as M2 minus M1 plus phi M3 minus M2 plus dash dash phi Mn minus phi Mn minus 1. This will give you the value of the total voltage between K and L, and hence if you see, this all will get cancel each other, cancel out. You will left only with phi Mn minus phi M1. This says that no matter how many numbers of metals will be connected in series, the overall contact potential is nothing but the difference between the work function of last metal minus the first metal, that is your psi KL. Let me put a question. Can we measure this psi KL by a voltmeter? To see this, let us go for a case number 2. So what I am interested in, to measure this psi KL or the equivalent contact potential between K and L by a voltmeter, considering this voltmeter wires are made up of same material. So the moment you take a voltmeter wires and connect the voltmeter leads and connect to the metals, there will be a contact potential found between this. This contact potential is what? Between Mu, which is the material of this wire, and M1. Similarly, there will be a contact potential here. And what you are interested in? You are interested in to calculate what is psi KL, or can you measure the psi KL by voltmeter. So, ultimately you are interested in to calculate psi BC. If you write the potential balance equation or KVL in this, then psi KL plus phi MU M1 plus phi Mn Mu is nothing but what? Psi BC. That is written here, right. So, you are actually applying a KVL like this. If you see that, we know what is psi KL from our basic understanding of the work function difference, right. Then psi KL is nothing but what? Phi M n minus phi M1, right. This is nothing but what? Phi M1 minus phi M u, and this will give you phi Mu minus phi Mn. If you see carefully, this all get cancelled, and hence the psi BC is what? 0. Meaning, the moment you are going to connect a voltmeter into this connection of series combination of metals, the equivalent voltmeter reading is 0. You cannot measure the contact potential by a voltmeter, because the voltmeter leads make a contact potential again with the materials, right. So, this is the case we have seen in PN junction diode also. In PN junction diode, if someone will say, can you measure a built-in potential between P and N, this is P and this is N, by a voltmeter? The answer is no, because whatever be the potential difference, the built-in potential coming into picture, like plus, and this is a built-in potential which is psi Bi. So, the moment you connect a voltmeter around a PN junction, across a PN junction, then this contact potential between N and the wire, P and the wire is exactly counterbalance the built-in potential of your PN junction, and hence the voltmeter reads to be 0. Now, what will happen if a voltage source is inserted into this configuration? If a voltage source is inserted into this configuration, the voltmeter reading is nothing but voltage source value. So, if you are going to rewrite this equation by inserting a voltage source into the connection, then ultimately psi BC is nothing but what? V source. That is what, if you apply a forward voltage or a reverse voltage, that voltage reading can be shown in voltmeter, but not the built-in voltage. We will apply this analysis in our basic fundamental block, which is called two-terminal MOS. A two-terminal MOS is a layered structure. It means I have one layer which is made up of metal. The another layer is semiconductor, and these two layers are separated by an oxide or an insulator which is called gate oxide. That is what the acronym came into picture, that is metal oxide semiconductor. Historically, the MOS structure used the metal gates and silicon dioxide as our silicon dioxide layer, right, or insulator layer, and silicon as substrate or body. So, this is substrate or body. But in recent fabrication processes and recent emerging devices, it is not necessary that the gate is made up of metal only. We can simply use the polysilicon gates also. Similarly, due to scaling limits, it is not necessary that the gate oxide is made up of silicon dioxide only. We can replace this by some other material having a high permittivity, let us say HFO2, or we can grow a stacked layers like SiO2 plus HFO2. Similarly, the body is not necessary is made up of silicon. It can be of 3,5 materials, it can be of strained silicon, etc. But to follow the continuity, we are using this acronym metal oxide semiconductor. It is a layered structure. If you see carefully, it is having two terminals, one terminal, another terminal. This terminal we named it as gate, and this terminal we named it as body, right. So, this structure is nothing but like a parallel plate capacitor having one plate is connected with gate and another plate is connected with body. The only difference is in this parallel plate capacitor, we do not have metal as another plate, we do have a semiconductor, and yes, semiconductor does have charges, it does have electron, holes or acceptor ions or donor ions, right. So, electron layer or so the semiconductor layer does have charges. So, the bottom plate of the capacitor is formed by the semiconductor, the top layer is made up of metal and it is separated by an oxide which is silicon dioxide. So, to understand thoroughly about this MOS structure which is called as MOS capacitor, we will jump or we will go for analyzing the MOSFET. Let us start with a basic understanding of flat band voltage. What will happen if we apply a voltage across this gate and body terminal? Let us consider a first case which is an ideal case, considering the gate and the body are made up of same material. Even this material is same as to contact the gate and body. For example, if we consider a p-type semiconductor, then this body and the gate is just nothing but an extension of p-type semiconductor. Then there is no charge pile up in this condition. Why? Because for every hole in the p-type material, there will be a immobile negative ion and there is a charge neutrality hold good. But this is an ideal one. In the practical case, what will happen? You have a gate which is made up of different material, you have a body which is made up of semiconductor, right, and the connecting leads or the connecting wires is made up of different materials, correct. It is like that, you have a metal, oxide and semiconductor. In this case, what will happen? The electron energy in the metal and the semiconductor is different because the work function will be different. If the work function of the metal and semiconductor is different, then there will be a charge transfer. In this condition, there is no charge transfer because we are considering the oxide is ideal and hence it will not allow the charge to transfer from metal to semiconductor or semiconductor to metal. Now, what we will do, the moment we connect externally like this, there will be a charge transfer from semiconductor to metal or metal to semiconductor based on the values of the work function. Consider for this case phi m is greater than phi s. If we go in our basic definition of work function, this is ER, this is EF, the Fermi level of metal, and this is phi m, right. Here we are saying the work function of the semiconductor is smaller, it means this height. So, obviously, the Fermi level will be higher than the Fermi level of the metal. If this is phi s, what will happen? There will be a charge transfer from the semiconductor to metal. If there will be an electron transfer through the external wire, then this near the surface, the semiconductor does have some positive charge, because ultimately what you are doing, you are actually extracting the negative charge from the semiconductor and giving to the metal. So, there will be a positive charge come into picture, right. If that is a positive charge, right, can you connect a battery in such a way that these charges will not pile up? That will give you the flat band voltage. The answer is yes, we can connect a battery in such a way that the charge will not transfer from semiconductor to metal. Or what is the amount of that battery? It is nothing but the difference between the work function of metal and the semiconductor, and hence if we connect a voltage VGB of amount phi ms, right, in such a way that it will restrict the flow of carriers from semiconductor to metal. So, this value is termed as flat band voltage, right. So, we are considering in this case that oxide is ideal one, it means there is no oxide charge in this case. So, oxide silicon dioxide is an ideal one, there is no oxide trap charges available. In that condition, the voltage value which you are applying at the external biases, gate and body, it will restrict the flow of charge from semiconductor to metal. That is called flat band voltage, right. So, the flat band voltages can be given by this. Let me summarize. In this lecture, we have seen what is contact potential. So, the contact potential is nothing but when two different materials will become in close proximity or in contact, there will be a potential developed such that under the equilibrium, the charge transfer will be stopped or will be blocked by that potential. We have seen what will happen when different materials will be in series. So, the contact potential is nothing but the difference of work function of last metal minus the first. We have also seen that we cannot measure the contact potential by a common voltmeter, right, because of the definition of contact potential, ultimately the voltage around the loop will be 0. We have seen that we have a basic fundamental block as a layered structure which is called a MOS cap. So, I have a layered structure which is metal, oxide and semiconductor. This acts as a capacitor when we connect a voltage between G and B, which is nothing but VGB. We have also seen that the contact potential developed between gate and body causes a charge pile up into the semiconductor, which we do not want, right. So, we want to remove that charge and hence we need to apply a voltage in such a way that charge will not pile up into the semiconductor. That voltage VGB is called flat band voltage. So, that voltage is called a flat band voltage, which is nothing but phi ms, meaning the difference of the work function, considering that oxide is ideal one. In next lecture, we will see what will happen if the oxide is not an ideal one. So, we will stop here for today. Until then, take care.